Hi everyone. So I'm trying my hand at creating video content for the class. These are going to mimic the content that we would have covered in class. Instead, I'm just going to create a video for it and post it to YouTube so that you can watch it at your leisure. Be sure to ask questions if you have them, either via the Zoom meetings or you can come into campus. My office hours are going to be held daily as I described in my email. So email me, come to Zoom, come to campus, whatever you have for questions. I'd be happy to answer them. We left off last time talking about how to define a system of units. Defining a system of units for the ease of calculation. I describe this approach because it's really fundamental to understanding why unit systems can be convenient for calculation and why they might not be. And also how you should go about in calculating things when it is convenient and when it's not. So, the first step to defining a system of units, and I covered this a little bit on whenever that was, Friday I suppose now. So this is a little bit of review and then we'll talk about it for specific unit systems. So the first thing is pick a fundamental set of dimensions. Step 2 is define fundamental units for that set. For each dimension, fundamental dimension. Step 3 is derive all other units from the fundamental units using dimensional analysis. I'll just say you have to define all other units in a dimensionally consistent way using nothing other than the fundamental units. So there's an optional step 4. Give other standard units a name. Okay, so for the sake of this discussion, there's a couple words I'm going to use. If I say something is a fundamental unit, I'm talking about a unit defined in step 2. If I talk about a standard unit, this also includes units derived in step 3. Or the ones named in step 4 for that matter. So I'm going to use an example here. Well, 2 examples, I suppose. Let's do metric and US. So in metric step 1, this is an MLT system. In the US, this is an FLT system. In metric, our fundamental unit definitions are the kilogram. Well, let me write those out. I don't just want to leave it. Kilogram, abbreviated kg, the meter, abbreviated m, and the second, abbreviated s. In the US, we have the, let me go ahead and back up. Please note, this is mass, length, and time for metric. Over here in US, it's going to be force, length, and time. So the force unit is going to be the pound abbreviated LB. The foot, abbreviated FT. And the second, let me try that again, And the second, abbreviated with an S. All right? The third step is going to have lots and lots and lots of examples, okay? For every single dimension, there must be a standard unit derived. So I'll just give an example. Let's do pressure. The first step is determine what are the dimensions of pressure. You want to determine what they are in the unit system that you are using. So if for metric, I'm going to talk about FLT. Whoops, my mistake. For metric, I'm going to talk about MLT. And for the US, I'm going to talk about FLT. For pressure, the MLT dimensions are M divided by LT squared. And for the US, this is going to be F divided by L squared. This means that the unit in the metric system is the kilogram per meter second squared. This is the metric unit. Okay? Over here, this is the pound per foot squared. And that's the US unit. This is really important, the process here, or just the idea rather than the process. We have 3 fundamental units in either metric or US, and every other unit is just a multiplicative combination of those units, everything. The important thing is, because a mass divided by a length times squared is a pressure, this is a pressure. That's pressure. Not only is it pressure, it's a specific amount of pressure. There's an optional step 4, and the optional step 4 is give it a name. In this case, the kilogram meter second squared is called a Pascal, abbreviated PA. This last step is optional and isn't always named. Like the unit doesn't always have some sort of name. For example, in the US system, you could give it a name. People call it the PSF, but you can guess what this stands for. This is just pound per square foot. It's not particularly a new name. That's just what it already was, the pound per square foot. So I'm going to go to the next page, and we're going to just go over a bunch of units in different systems. The first thing that I want to consider is, well, if we're in an MLT system, like metric, what is F? What is the F unit? Well, I know that F is equal to ml over t squared, which tells me that this is the kilogram meter per second squared, since these are the fundamental units. Kilogram, meter, and second are all fundamental. That means this combination of them is standard. This is a standard unit. This is given a name, so this is step 3. Step 4, this is called a Newton, abbreviated with an N, and it's a specific amount of force. When you push on something, you can express that quantity in terms of newtons. In the US, I might consider, since it's FLT, what is M? Or what is the M unit, I should say. Let me put question marks on both of those. What is the M unit? Well, using step 3, we have that M is equal to FT squared over L. This is the pound second squared per foot. In the metric system, in the US system, this equal sign isn't particularly appropriate, so I'm going to go ahead and remove it and replace it with an arrow. The pound second squared per foot. Thing to realize, this is a specific amount of mass. And, well, here's where it comes down to it. Does this have a name? Most of the time on the US side of things, No, it does not have a name. This is an exception. This does have a name. It is one you likely never heard of before you went to school and likely haven't heard of still. This is called a slug. It is not really abbreviated, so that's that. A slug is a pound second squared per foot. Okay, so that's a good thing. Let's talk about the next one. Let's go for energy in both systems. Okay, so in energy, in MLT, we have that energy is dimensionally ml squared per t squared, which is going to give us kilogram meter squared per second squared. This is called a joule. And over here, we have that energy is F times L, which is going to be the foot pound or pound foot, if you like. Step 4, there isn't a common name for this, not a different name. We just call it a foot pound or a pound foot, either one. That's the standard unit for energy in the US system, and it doesn't have a separate name. And it's not really used very much. If I talk about energy units that are commonly used, the pound foot will not really appear on any lists. The only value of it is that it is standard and therefore convenient for calculation. We'll talk about that in a little bit. Over here, the joule is standard, and it's used all the time. If you've taken physics, then when you talk about energy, you're talking about it in joules. We could keep going, but this process ought to be clear. Pick any unit like power, or any dimension, I should say, like power, write down the dimension, ml squared per t cubed, then use that to get the unit, kilogram meters squared per second cubed. This is the standard unit, and then you can look up if that has a name. In this case, this is called a watt, abbreviated with a W. Over here, power is FL over T, which is going to give us the pound foot per second. This has no common name. That's it. That's the process to determine what is a standard unit. The next question is, why do we like standard units? Why standard units? There are two calculations that I want to consider with you. The first one is F equals ma. This tells you if you have a mass, m, accelerating at a rate given by a, then the force that was exerted to create that acceleration is F. So I'll give you an example. Let's say you got a block. This, for those of you who know more physics, like frictionless, everything's simple. You have a block and it has a mass of, we'll say, 5 kilograms, and you exert a force, well, no, let's say this. You observe that it is accelerating to the right at 5 meters per second squared. What was the size of the force that caused this? Well, F equals ma, which is equal to 5 kilograms times 5 meters per second squared, which is equal to 25 kilogram meters per second squared. And what I can say right away is that this is a standard unit. Because I used standard units, I'm going to get a standard unit. And as a result, I just need to know what is that called. And we up here said that was called a Newton. So this is equal to 25 newtons. The way this actually tends to work is you just know what the standard units are. You know kilogram is standard for mass. You know meters per second squared is standard for acceleration. And you know that a mass times an acceleration gives a force. You're expecting a force. So if you're using standard units, you just get the standard unit for force. And if you know that's a Newton, you don't have to think about how the units interact. How do the units interact? You don't need to know. You just need to know that a mass times an acceleration is a force, and you need to know that these are the units for those things, and they are standard. Use standard units get standard units. That is the point. You do not need to think about the unit interactions. Now let's talk about F equals ma with US units. I'll just say from a physics class, I would anticipate that anyone who has taken physics does not know how to calculate this without converting to metric. Okay? So, that might not be entirely true, but let's go through it anyway. If I was to tell you the mass of the block, what mass unit should I use? What mass unit should I use? Well, what I said over here was use standard units, get standard units. So what mass unit should I use? The standard one. What is the standard mass unit? It's called a slug. The standard mass unit is a slug. And if this has a mass of 5 slugs, and you observe it accelerating to the right at 5 feet per second squared, then it's just true that F equals ma. That's equal to 5 slug. Let me try and fix this. 5 slug times 5 feet per second squared is 25 slug feet per second squared. But once again, I'm not going to worry about the units here. Here's what I know. I used the standard mass unit. I used the standard acceleration unit. So I get the standard force unit. What is the standard force unit in the US system? It is the pound. So this is how you do it in general. But the problem is, if you're doing a US problem and they give you normal quantities, they are not going to tell you the mass of the object in slugs. If they did, it would be convenient. The slug is the US kilogram, so to speak. But they won't, because it's not in common use. So what will they give you instead? They will likely, let's make sure my eraser isn't too big, they will likely give you the mass in pounds. And we might want to note that it's a mass by saying pound mass, although I'll talk more about that later. They'll give you the mass in pounds, and that's a little bit odd. In that situation, what do? Well, all of this is garbage. None of this matters, so let me erase it all. Oh my gosh. This is 5 pounds. This is definitely, pounds mass. This is definitely equal to 25 pound mass feet per second squared. But this is not standard and is not equal to 25 pounds. Absolutely not. Because this isn't the standard mass unit. It's just not. So we need a different approach. Well, the appropriate thing to do is to convert pounds mass to slugs so that the calculation can be performed. Okay? Let me ask you a question, though. If I'm going to convert, let's ask, how many slugs are there in a slug? Or vice versa. I'm going to use a little subscript m here, because I'm going to do that the entire time. Pounds mass in a slug. Well, let me first ask you the following question. How big is a slug? Well, I'll tell you precisely how big a slug is. A slug is the amount of mass that if you exert a 1 pound force on it, it will accelerate at a rate of 1 foot per second squared. That's how much a slug is. Precisely. Similarly, how big is 1 Newton? 1 Newton is the amount of force that if you exert it on a 1 kilogram object, it will accelerate at a rate of 1 meter per second squared. That is the relationship between these quantities. In the formula F equals ma, they have a 1 to 1 to 1 relationship because 1 times 1 equals 1. For standard units, you don't have to For standard units, you don't need to concern yourself with the unit interactions. You just know that it gives you the right unit. So, in terms of understanding this, we need to understand F equals ma and get some sort of sense for it. Okay? I have a question for you. If you exert, oh my goodness, eraser. If you exert a 1 pound force on a 1 pound mass object, then how quickly will it accelerate? And I will tell you a situation when this happens. Anybody know? When do you exert a 1 pound force object on a 1 pound mass? When do you exert a 1 pound force on a 1 pound object? Do you know of any situations where this is definitely the case? I do. What about force of gravity in free fall? I know that in that situation, you have a 1 pound mass object with a weight force of 1 pound acting on it. And if nothing else is acting, I know it accelerates downward. Do you know how big the acceleration is if an object is in free fall? You might know it in meters. It's 9.81 meters per second squared. If you convert that to feet per second squared, you get 32.2 feet per second squared. So, 1 pound mass, how shall I say this, times 32.2 feet per second squared is equal to 1 pound. This is a situation we know. We know in free fall, a 1 pound mass object has a 1 pound force acting on it because 1 pound is actually the weight. That's what 1 pound is. It's the weight force. So we have this relationship instead. This might be familiar to you. This formula is W equals mg. And you might think that this formula doesn't line up because 1 times 32.2 is not equal to 1. No, it does line up perfectly. What you're thinking is that it doesn't line up, but that's because the units don't line up. A pound mass foot per second squared is not equal to a pound. A slug foot per second squared is equal to 1 pound. What we just discovered based on this formula is that 32.2 pounds mass feet per second squared is what's equal to a slug. I didn't quite say that right, did I? 32.2 pounds mass feet per second squared is equal to a pound. This is the same equation as this. They're the exact same thing. I've simply rearranged them. Can you take these two equations, these two, to figure out the relationship between a pound mass and a slug? You ought to. I mean, they have a lot in common. You would simply find that there are 32.2 pounds mass in one slug. This equation is important, this conversion factor, if you want to have an intuitive sense of how much a slug is. Because I imagine, if you grew up in the US or if you've lived here for very long, you kind of have an intuitive sense of how much a pound is. There are 32.2 of them in a slug, so it's quite a lot. It's quite a lot of mass. That is, well, I guess that's all I really want to say about that. I don't want to talk about the pound mass too much, all right? So here's what we can say about the pound mass. The pound mass is the amount of mass that weighs a pound. That's what a pound mass is. 1 pound mass weighs 1 pound. On Earth. That is the actual definition. And so now I want to talk about another formula. To calculate the weight of an object, wow, that word got away from me a little bit, of an object based on its mass use W equals mg, where this is the weight force, this is the object's mass, and this is what is called the acceleration due to gravity. This formula is what we're going to spend most of our time working on. W equals mg. And it's perfectly appropriate in this situation. Let me ask you, what is the acceleration due to gravity on Earth? Well, it's about 9.81 meters per second squared, which is, if converted, equal to 32.2 feet per second squared. That's important to realize. So if I were to ask you, what is the weight force of a one slug object? Well, one slug, which is the mass, times 32.2 feet per second squared, which is the acceleration due to gravity, is equal to the weight force. And just multiply this out. You're using standard units, so you're going to get standard units. This is 32.2 pounds. One slug weighs 32.2 pounds. If you try and say that 1 pound mass times 32.2 feet per second squared equals 32.2 pounds, you are wrong. This is not correct. Why? 1 pound mass does not weigh 32.2 pounds. I'll look at the top of the page. 1 pound mass weighs 1 pound. Pound mass is not standard. Don't use it. If you have a mass and you need to find a mass, you have two options. Option 1 is on the previous page. Convert using this formula. I should have underlined that rather than circled it. I got too many circles going on. Okay. This is a conversion factor from pounds mass to slugs. Pound mass is not standard. Convert it to slugs. Or use W equals mg to calculate the mass in slugs. Let me give you an example. An object, I'll just say a 5 pound object. A 5 pound object has what mass in slugs? Well, first of all, when they said 5 pounds, were they talking about force, that is weight, or were they talking about mass? Well, a layperson is talking about either one, and you can't really tell. My default is to say that that is a force, because pound is a force in general. It is the weight force. So what we do is we use W equals mg, where 5 pounds is the weight. 5 pounds divided by 32.2 feet per second squared gives the mass in slugs, in standard units. Let's see, I don't think I have a calculator in a convenient location, but you could calculate this. 5 divided by 32.2 slugs. Second option is you take this to be a mass. The mass is equal to 5 pounds mass. Do not use this number in calculation, and instead just multiply it by the appropriate conversion factor. There are 32.2 pounds mass in one slug, and this gives the same result. 5 divided by 32.2 slugs. 2 options. Okay, so big takeaways. Use standard units. Get standard units. That is the big important thing from all of this. We just spent a lot of time talking about how pound mass is not standard. I'm just going to talk to you for a minute before we conclude this video. Knowing standard units is helpful. And the reason is, when you're doing complex calculations, you can simply analyze the formulas from a dimensional standpoint. And if you understand the dimensions of the formula, you don't need to worry about units very much. If you use standard units, you will get standard units. If you know you're plugging in a bunch of stuff, and you know the result is going to be a power, and you're in metric system, then you just know it's going to be watts. If you use kilograms and meters and seconds, and only units that are derived from kilograms, meters, and seconds, then when you are done, you are going to get a combination of kilograms, meters, and seconds. That combination, if the equation was dimensionally homogeneous, will be that of power. And the standard unit of power is watts. So, you might have noticed in your in your physics classes, if you've taken them, you don't worry about units very much. And the reason is you're working in metric. And all the given information is standard. That's what it comes down to. The reason the US system is less preferred is not because of factors of 10. It's because the standard units, those convenient for calculation, are not the units in common use. That's the only reason. Factor of 10 has, I'll say, plays a role in what makes it convenient for when you do have to convert. Yeah, I'm not going to write more. Use standard units, get standard units. What if you don't have standard units? Convert to standard units. If you don't have, I'm going to create some more space here. Oops, eraser. Eraser. There we go. If you don't have standard units, convert. Okay. In the future, I'll show you some example problems. I'll post some shorter videos about examples, and we'll work from there. All right, I hope this is helpful, and I will see you all at a later date.